All right, done.
All right, we're good. Go ahead.
Well, welcome to Tom Talks. My name is Tom Simpson. I work with McHenry County Conservation District, and today we're going to talk about everything you ever wanted to know about soil, but we're afraid to ask. You've got your chance today to ask. First, a little drama.
Hey, Tom, we don't have the audio, so I think you got to check the boxes when you share the screen.
Hold on. I always forget something. Okay, so we stop share. Yep. Always. Okay. Yeah, here we go. Now, did anyone? So is everyone hearing me now?
Yes.
Oh, good. Everything you ever want to know about soil, but we're afraid to ask, you'll get your chance today. But first, we're going to start with a little drama.
Elliot Ness here, Inspector, Bureau of Homeland Insecurity. Working undercover today. Our Forensic Science Unit, the FSU, has informed us that the very ground you walk on is changing as we speak. Tiny particles are moving downward after every rain. Billions of tiny creatures have taken up residence in every shovelful of earth. Tons of decomposed waste are being added every year to every acre of ground. Animals of all sorts are burrowing, digging, crawling, and slithering through the soil. Miles and miles of roots and interconnected fungal fibers are slipping, pushing, probing their way through every crack and crevice in the soil. Frankly, people, it's a mess down here. And we put our best agents on the job. Oh, yuck, another millipede. It's crawling up my leg.
So, as Elliot said, soil's a happening thing. Probably nothing in the popular imagine seems more stable and dull and unmoving than soil, but when you start to look at it, you see that it is indeed a very dynamic thing in nature and something that is just a joy to look at. So I'm going to try to communicate some of that joy and some of the interesting things you can learn about soil today. Soil starts off, most soil is some sort of parent material. Let's say just a big block of glacial till, a mix of clay and silt and little pebbles. But over time, it separates into these layers, and we'll call those horizons and give them names and descriptions. How does that happen? Well, first let's just talk about the setting in which all of that happens. There are 5 factors of soil formation, and this really comes from a very, very wise man who wrote a book called Factors of Soil Formation in 1941. And to this day, I've never read a better first half of that book, which sets up soil as a dynamic body and how it changes over time. I've never read a better description than Hans Jenny's first part of that book. The second part is more technical, and some of that has become a bit outdated, but the first part is beautiful, beautifully written. These 5 different factors: climate, parent material, relief, organisms, and time. And when I first learned about this in school, I just thought this is an excuse for a, name the 5 factors of soil formation, and then they give you 5 blanks to write them in, or it's a question where they have 8 things down there and they says, check the ones that are not factors of soil formation, and then you memorize it and you go on and you think nothing more about it. But as I started to work with soils and research, And in teaching after getting out of school, I kept coming back to this as just a fundamental framework for interpreting soils in the field. And I hope that comes through today, mostly in the second part of the presentation when we go outside and start looking at things. And then there are 5 processes of soil formation. So if that was this, if the factors really describe the setting in which things happen, the 5 processes are the actual things of how soil forms. So we have primary minerals that are breaking down. Primary minerals like feldspar and mica, which form as a liquid rock. Lava cools. Lava or magma below the surface cool and crystallizes. Those primary minerals are formed under very high temperatures or pressures, and they're unstable at the Earth's surface. I mean, you think of rocks as permanent, but they're not. They start to break down, and they release their constituent parts into the soil solution called ions. Those ions will then spontaneously come back together and form other crystals, and we call these secondary minerals or clay. So the word clay in the popular imagination is just a gooey moldable substance, but when it's in soil science, that refers to the particles that make up that substance. They're very, very tiny in size, but also to our particular set of crystalline structures, clay mineral structures that form in the soil, so under very low temperatures and pressures in the soil, and are more or less stable in the soil. Sometimes they transform from one kind of clay to another, but they never turn back into a feldspar or a mica. And then we have movement of things in the soil. Again, everything seems to be stationary in soil when you look at it on a human time scale, but over even just centuries to thousands of years, lots of things move around in soil. Just 2 things here. We're talking about clay. That's the colloid. Colloid, just a name for a tiny particle. That you can imagine these lines would have been just horizontal in that original block of parent material, but over time, they take on a particular distribution because they move in the soil. Those clay particles move. Likewise, things like calcium carbonate dissolve and move. The CO2 curve here is really describing calcium carbonate and how that formerly horizontal line has become a curved line, the calcium carbonate typically migrating lower than the clay. This is an extreme example of change in soil. These are northern forest soils. I worked with a lot of soils that look like that up in the Upper Peninsula of Michigan back in the 1980s. Oxidation reduction, really here could refer to lots of different chemical reactions, but here really referring to the change in oxidation state of iron compounds in the soil. That's especially important because iron is a very powerful pigment. If you were once fancied themselves an oil painter, as I've fancied myself many things, but once I did, and you start looking at the pigments on paint, you find lots of metal oxides used as pigments because they're very powerful colors. Iron, when you rust it in contact with lots of oxygen, turns orange. Most of us have noticed rusty iron turns that orange color. That's because as iron combines with abundant oxygen, it forms an oxide that's very yellow and orange, and sometimes reddish in color. The oxides that form under very low oxygen, such as in a saturated soil, are more gray in color. They're also water soluble, but they're more gray in color. So we can look at those colors and judge seasonal saturation. Even if we encounter this wet soil in August when it's dry to the touch, the colors will tell us that it's seasonally saturated. And here in the middle, you can see a soil that's a little bit of both. Somewhat brighter colors, at least for a soil, showing oxidation, the grayer colors showing reduction. And the addition of humus, this is probably the fastest operating of all soil processes. It takes only a matter of years or decades for organisms growing at the surface of a sand dune to start to change that very upper crust of the dune and start to add organic matter to the soil. Most of that organic matter is added by the roots themselves because they're oxidizing below the surface in contact with the soil under slightly lower oxygen conditions. The surfaces often are fully oxidized or burned off historically around here. So it's the roots that are the major adders of organic matter, but that's probably the fastest operating process. And then you have animals like worms, most of which are really European worms in our soils today, but we have things like 13-line ground squirrels and ants, which were probably the dominant soil movers in our pre-European settlement landscape that are mixing that organic matter constantly in the surface soil. So we end up with this layered structure after, 10,000, 18,000 years. It's not a block of material that's the same from top to bottom anymore. It's now separated into layers, and we give those layers letters, A, B, and C. And we'll interject a different layer here in a second. We'll call that the E horizon. But important here just to think of this as the profile. That word profile is used to describe this sequence of layers in a soil. So when I talk about the profile, I'm talking about all of it together. When I talk about a horizon, I'm talking about a single layer. When we name the horizons based on really the processes or the process of formation. So the O layer is really what's above what we think of as the soil itself. It's that layer of undecomposed organic matter, a very partially decomposed organic matter sitting on top of the mineral soil below. The A horizon is the zone of mixing. Often much of the organic matter there is contributed by roots, but some of it from the surface that's brought down into the soil by organisms. Mixing together the E horizon, that mysterious layer between the A and the B, is the zone of leaching. So the zone where the movement of materials is the dominant process. So here, A, dominant process, organic matter addition and mixing. Dominant process here, leaching. Dominant process in the B horizon is the accumulation of clay and carbonates leached from the upper layers. And we use C to designate those zones that have really not changed much from the original parent material. So in the Chicago area, usually we're talking about a glacial material in the upland landscape. But if we're in a sedimentary basin, it could be just clay sediments in the bottom of a basin, or it could be alluvial sediments around a stream. We'll look at both of those in the second half of the presentation today. So we have layers, and we designate the layers by a letter. Each of them has a definition. I want to talk a little bit about some of the properties of the soil and start off by talking about the acidity and alkalinity. It ends up being quite important to how soil forms, and so I'm going to give this a try today. Sometimes I skip this part, figuring it gets into a little bit of chemistry and people's eyes glaze over, but we're going to try again today. Never give up. So clay crystals are layered structures in the soil, like little people. You can imagine them as little pieces of plywood that along the edges of those layers have negatively charged what we call exchange sites. And we call them exchange sites because calcium ions and sodium, if it's in the soil, or magnesium, these ions that are positively charged will cling to those negatively charged exchange sites. And because our glacial sediments were very rich in calcium, because the parent rock that was ground up to make the glacial sediments was dolomite, or calcium magnesium carbonates, lots of calcium in the soil, and the clay crystal is saturated with these calcium ions. But when you put it in the surface soil under natural weathering conditions, well, excuse me, this is where I'm trying to make it easy for you. But we're going to call calcium the good guys today. But you put it in a weathering environment of the soil where acid rainwater is filtering down through the soil, and you have lots and lots of hydrogen ions that are bathing those clay crystals, and we're going to call the hydrogen ions the bad guys today. I've known a lot of good hydrogen ions in my day, but we're going to call them the bad guys today, and the calcium ions the good guys, and we'll see how these two interact with one another. What happens when you bathe that soil in hydrogen ions is they start to displace the calcium ions and push them off of the clay crystals. And once those calcium ions are free in the soil solution, they start to move downward. They're leached out of the surface soil. So the bad guys are kind of winning here, and the good guys are being leached downward in the soil. And the reason that's both caused by acidity, and as the lime moves out of the soil becomes more acid. It's the opposite of reasons why farmers put calcium carbonate or lime on their soil. When lime dissolves in water, it forms a strong base and a weak acid. So the net reaction is to make the soil more alkaline, or sometimes called more basic in pH. So this loss of calcium is both caused by acidity, and it induces more acidity in the soil. And all of this is a sort of necessary background for understanding this fundamental difference between soils formed under prairies and soils formed under woodlands. When we look at the pHs in those soils, the concentration of hydrogen ions, we find that soils in prairies tend to be higher in pH because they recycle calcium much more aggressively to the surface. Grasses have what's called luxury consumption of calcium. Their leaves are chock full of calcium. And when they're either decomposed or are burned off by a prairie fire, that calcium comes back to the surface. Physical processes of leaching move it downward. Biological processes of uptake and storage move it upward. And that balance maintains a pretty even pH profile through a prairie soil, at least most prairie soils. So you have sort of called circumneutral. They're maybe very slightly acid or very slightly alkaline pHs through much of the soil profile in prairies, whereas in woodlands dominated by oaks, you have a very weak uptake of calcium because oaks just don't need a lot of calcium. They don't store excess amounts in their leaves. Therefore, when the leaves burn or decompose, they don't contribute it back to the surface. The physical process of leaching, however, is always acting, and you have a net acidification of soil over here. And with prairies, you have a balance between the two, and so the soils stay around neutral or something like that. I mean, it depends on the prairie. But at least a net acidification of woodlands in relation to prairies. And this comes from a study I did with a graduate student back about 20 years ago. Doesn't seem that long ago, but about 20 years ago, we looked at many, many high quality savannas and woodlands and prairies in McHenry County, and you can see that the oak savannas and woodlands here in the center have the lower pHs, the more acid pHs. Prairies somewhat higher, near neutral. Neutral is 7. This is the sugar maple forest down below, which typically is called a mesic forest. The sugar maple forest down below, pH is somewhat elevated there because maples have a pretty high uptake of calcium, recycle that back to the surface. And you see that it's sort of intermediate between the oak woods and the prairie. And this pH is important because it controls the movement of clay. Clay particles, as I said, have these negatively charged exchange sites. Well, the calcium is what's called a bivalent ion, means it has 2 positive charges, and it tends to glue the little clay crystals together. In fact, it's one of the basis for soil structure we'll talk about in a few minutes. Structure, the way the tiny particles in soil cling together into larger clods called PEDS. Calcium is very important to building soil structure. So when you have higher pHs and lots of calcium in the soil, you tend to hold those clay particles together into what's effectively a larger particle, and they don't move. They don't translocate in the soil. The water moving down the soil can't pick them up and move them because they're not individual little clay crystals. But when you saturate that soil with hydrogen ions, the calcium is bumped off, and the crystals now are individuals and subject to leaching. So we get moved, not only is the woodland soil more acid, but because it's more acid, the clay starts to migrate and move downward in the soil. So we'll find that not only are woodland soils more acid than prairie soils, but that they also have more translocation of clay, and we'll look for that in the horizon structure of the two here in just a few minutes. E-horizons, a zone of leaching, will form in woodland soils and not in prairie soils. Soil texture, another property of soil, and there's so much about soil that can look so technical at first glance. I mean, even this chart on the right-hand side, which is trying to make soil texture simple, ends up, in my mind, making it look pretty darn complicated. Consistently through this presentation, I'm going to give you an ecologist point of view on that. That doesn't mean that there aren't other points of view on soil, and a soil scientist may have a very different point of view. This is an ecologist speaking, and it's the sort of things that I look for in soil. So when I'm looking at soils, what I'm really doing is breaking it really down into these 4 groups. The red circles are soils derived from glacial tills. We have a little key up here in the upper left. So it's going to be silty clay loam, silty clay. So I'm not really going to spend a lot of time trying to tell a silty clay loam from a silty clay from a clay loam. That's really, really hard to do, frankly, in some of the clays that are very close to that in their percentage of clay content are really hard to tell apart, but it's not important to me. I'm identifying an upland landscape, rolling terrain. I see this range of soil textures, and I see little pebbles in it. That's a glacial till. That tells me something very important about that. Those tills, subject to leaching over long periods of time and creation of E-horizons, will create silt loam textures. So those two together work together in my mind. That's what I'm looking for in an upland landscape. An upland landscape, I suspect, is a moraine and glacial till. I'm looking just to tell the difference between those two. I'm not starting from scratch and just wondering what on earth soil texture it is. I'm looking to tell that difference. Likewise, if I'm in an old lake basin, I may be down here in a clay texture. And that's when we'll actually see one of those here a little bit later in the presentation today. And when I'm encountering lots of sand and grit and gravel in the soil, I'm over here in an ice contact soil. This is the soil textural triangle, which initially looks very confusing, but is kind of a handy way. We don't normally work with 3-cornered graphs, but to look at this triangle, the percentage of sand increases in this direction. So 10% sand goes up this way. 50% this way. Clay content goes up as I'm going up this way. And so 10% clay, 10% clay goes across the chart, and silt comes down this way. And so 10%, 50% silt. Now that may be a little bit confusing, but if you get the PDF and look at this for a while, it's pretty handy. Our clay textures are right about in this red circle. So even though they may go back and forth between clay loams and silty clay loams and silty clays, they're all really clustered together. They're very close to one another. Likewise, when they leach and become silt, they're increasing in silt. They're moving downward, they're decreasing in clay, and so they're moving over here into a silt loam. The clays in a lake basin are usually up here. They're silty clays or clays, 2 textures, but really one little area on a soil textural triangle. And our outwash ice contact soils are really down here, lots of sand and not much clay and often gravel, which really isn't a part of the triangle. This is just for particles, sand, silt, and clay size. So clay is the tiniest of particles. It's less than 0.002 of a millimeter in size. Sand is the largest, that's greater than 0.05 of a millimeter. You can feel the grit in sand, even very fine sand, 0.05. You can start to feel the grit between your fingers. Clay is much too small to see, and silt is what's in between, and most of our silt is created by the grinding action of glaciers. Now we know where clay comes from, that's a secondary mineral, and sand are really little fragments of primary minerals, mostly quartz in the soil. So they're size particles. They're also sort of genetic origins of particles that make up our soils today. So soil texture can seem really complicated. It's not that complicated, and particularly not that complicated when you're in the field and you're making only a few distinctions. Soil colors, again, these pages in a Munsell soil color chart, you get a book and it's got about 25 of these pages, and what could be more complicated? We've got about 40 different color chips here. And this could be very confusing, but it's not so confusing. When you're looking at an A horizon, you're generally somewhere down in these 4. Woodland soils that are less organic rich are generally on one of these 2. Prairie soils are down here, or soils in wetlands can be here, or it can be on the next page I'll show you. They get very black. When I'm in a well-oxidized soil, a soil that matures in an oxygen-rich environment, the B horizons are generally over here. When they when they get water saturated, they just move in this direction, and then one of these 4 chips here. So once you learn that and you're in the field, you're looking to make those distinctions. You're not just wandering back and forth through pages in the books and back and forth through every chip on the chart. You're looking to make those meaningful distinctions between well-oxidized colors and not well-oxidized colors, between organic rich soils and soils that are less organic rich. And if you're looking just for those things, it becomes much simpler and more straightforward. This is a chart we use when we're talking about wetland soils that are very gray from prolonged saturation and reduction in the metal compounds in the soil. And you can get almost jet black colors because of high organic contents in the A horizon. Organic matter decomposes more slowly in wet environments than in dry environments. So it's generally in higher, the surface soils are higher in organic contents. I mean, frankly, I don't use this chart very much because for me as an ecologist, the meaningful thing is to identify a wetland. I'm not particularly interested in the differences between these chips up here. I'm interested that it's a gley, what's called a gley. The soil is dominantly a very gray color, showing prolonged saturation. I may look for things called root oxidation models, which we'll see a little bit later in the presentation today. A phenomena that happens when wetland plants are growing in this gleyed mineral soil. Soil structure is something I'm not going to talk about a lot today, and it's because when you work in natural areas of soil structures, the aggregation of particles into PEDS, PEDS, one of my favorite words from soil science, short to the point. When you aggregate those particles, like clay, silt, and sand particles, into lumps, or what you might have called clods, what I would have called when I was a child, now they're PEDS. In the A horizon, when you have lots of organic matter, typically the PEDS are small, sort of granular, I think like grape nuts. I used to eat grape nut cereal for breakfast. When you're down in a B horizon, where you've got more clay, the structures are typically blocky and prismatic. There are lots of subcategories of subangular, blocky, and large and small, and the firmness and of the PED, but let's not worry about that today. Blocky and prismatic structures in the B horizon. The E horizon will have small, sort of weak subangular, blocky structures, or platey. I'm not sure why this diagram shows the plates like giant flapjacks. They're generally pretty small. Sometimes I used to like to make biscuits, and if you knead biscuit dough for a while, and then you cook it, you can see a sort of platey structure to the biscuit, a layered structure to it that's a little bit like E horizons. Sort of a food analogy there. And when you have like gravels and sands where those big particles really don't cling to one another, you call that a single grain or structureless or single grained structure. And if you drive over a soil with a car long enough, it will compact it in more or less a massive brick. And we call that structureless or massive. So I'm not going to talk much about structures today, but it's an important thing to remember when you break down soil structures. Soil stops working. Water doesn't go into it. Roots don't move through it. Plants die that are growing in it. So soil structure is very important to farming and to gardening. Not so important to me because I'm generally working in natural areas in places where the soils have not been compacted. I'm going to show you this description. It goes on for 3 pages here, and if anything could scare you about soils, this would be it. Most people tend to read this like a book, and you start off, it says this Blount series, soils are, we might think of these as like the species of soil. The Blount series consists of a very deep, somewhat poorly drained soil, blah, 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 goes on, and then you can read here, and you can read the paragraph on the A horizon, the paragraph on the B horizons, the paragraph on the C horizons, and it all gets very confusing. But what I want to show you today is what to look for. This is what you would find if you looked at a map. Jackie, when we were talking about ecological history of sites, she talked about finding these soil maps and soil descriptions online. And you can, but how do you use this? It just seems so confusing, but what you're going to do is you're going to look for particular things. So we're going to look for texture that are highlighted in blue, colors in red. And I just bolded the acidity of soil and then the gravel content. So these silt loam, so let's just look at texture from top to bottom. Silt loam, silty clay, clay, silty clay loam, clay loam, clay loam, clay loam. So that may already sound familiar. That's what I described as a woodland soil developed in glacial till. So I read a soil description from top to bottom, not from side to side, because by the time you finish reading that whole paragraph in the A horizon, you've forgotten the first part by the time you get to the B horizon. So read it vertically. We see a progression from textures from relatively little clay to more clay. Let's look at the acidity of soil as we go downward. It goes slightly acid, strongly acid, slightly alkaline, moderately alkaline, moderately alkaline, moderately alkaline. So we see it's leached and more acid at the surface. Not surprising given what we already know about soils and the physical process of leaching. That's what we would expect to see. And the colors, a dark grayish brown is a 4-2 is not a particularly dark A horizon, but the darkness that's there is a result of organic matter. The P over here tells us a plow horizon. So this was actually done on an old farm field. Had we encountered this blount soil before farming, it would have had a 2-1, a very, very dark brown color to it. But it's lost a lot of the organic matter by mixing with the plow for probably a century. And as we go down in the soil, get into the B horizons, we're seeing these colors, these gray colors, that what's on the left-hand side of the color chart. We'll come back to this later. Grayish brown colors, grayish brown colors again down here, grayish brown colors, and that transition to the C, we denote a transition by putting both big letters there. So that's telling us it's a wet soil. So we know it's leached, it's wet. And we see what's called clay films here in the soil. That means soil clay is migrating downward in soil and then being deposited on the surface of PEDS. This is a hard one to show in a video, but if you're working with soil, you break the PEDS of the B horizon apart. They often look like they've been coated. You break the PED open and you see a different color on the inside than the outside because they're covered with a film of clay on the outside. So reading this from top to bottom tells us about change. We get down here to the C horizons. Remember, this is the zone of parent material. The D is a letter they added since I went through school. That just means an impermeable zone. Roots just don't go down into this. So below 30 inches, roots wouldn't, there's nothing to get to there. This is some of my problem with some of the, what I think of sort of generalized pictures of prairie root systems going down 6 or 7 feet in the soil. They don't do that in these kind of soils. There's no point to it. They need a drill to get into this stuff. You need a pick to dig in it. So 30 inches is about the limit. So we're looking at these tills getting down to about 10% gravel contents, the clay loam textures. That's just the texture of the original till. Massive structures here in the lower part of it, massive because it's still what it was before any changes due to root growth. This is whether I do this in my head, I'm doing it for you in a chart. This picks out the important things. And again, read it vertically. Look at the changes in textures. Silt loam, silty clay, clay, silty clay loam, clay loam, clay loam, clay loam. And flip back and forth here. They're all right here. They're really not changing that much. They're all right here. It's a typical glacial till. It bounces back and forth between these. It sounds like it's changing a lot, but it's not. They're all very consistent textures, only this one has been leached to clay at the surface. The colors are, as you go downward in the soil, look for those chroma 2 colors in the B horizon, the dull gray colors, here, 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 here. All of those showing water saturation in the B horizon. That's what you're looking for. We have a little oxidation, a little more oxidation in this B horizon here. And look at the shift in acidity, slightly strongly back and forth here, but acid in the upper profiles becoming alkaline down below. It's exactly what we expect given the physical process of leaching. So you can take that big, complicated, confusing soil description and break it down into something that's that makes sense in terms of what we understand about the processes of soil formation. Remember the color, just to show you those chroma 2 colors over here. So maybe I didn't go through this. In a Munsell chart, as you go this way, you're taking the pigment. This is the spectral color. You take the pigment out. Just imagine mixing painting. You're taking the pigment out, and it gets more and more bleached in color. In this way, we're just adding black, and the soil becomes a shade of that tin, eventually coming to here, which is very, 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 very dark brown. So chroma 2 colors are those colors in these 2 rows, and from here on up, they're really showing water saturation in the B horizon. That's why they're important. That's why we're looking for those chroma 2 colors. We just don't wade into a soil description without thinking about it. We're always looking for something. These are the well-oxidized colors over here. These are the poorly oxidized colors over here. These are the colors of our organic-rich A horizon down here. And so, you know, sweating the details of which one of these chips is not the important thing. It's getting it into this category of well-oxidized soils. I don't know how I ended up with the squiggle there, but we're not going to worry about it. It's a little artistic flair. I wanted to talk a little bit about soil orders because these words have sort of crept into the popular vocabulary. And I hear people talking about alpha sols and mollisols and sort of using them as ironclad categories. And that's really, you know, some things work well in a textbook, then when you go out into the field, they start to work less well. The strange terminology alpha sol, which isn't a word most people heard of when they were growing up, strange terminology seems to creep into science to sort of scare people away as a sign of authority, but it's actually really just a way soil scientists try to create an unambiguous language for talking about soil among themselves. That does create barriers for people on the outside to understand it, but it wasn't deliberately done for that purpose. It was done in order to create a relatively objective, factual language of soils so that people in China can talk to people in America, can talk to people in South America about soils and talk in a language that's mutually understandable. So we have alpha soils are an order, a high-level classification of soils that more or less correspond to soils that form in woodlands. They typically have thin or A horizons that are not especially black in color. They have a well-developed zone of leaching for reasons we've already talked about. Acidity mobilizes the clay that migrates downward, and you have a clay-enriched B horizon. Classic alpha sol soil. The mollisol is again, we're going to see some soils in the later part of the presentation that look like this that are not grassland soils, but classically it's a grassland soil. It has a deep organic rich A horizon because grasses tend to have very fine root systems, and those root systems grow out and die back and grow out and die back very dynamically through the growing season. They add a lot of organic matter to the soil, and they produce this deep, dark A horizon. They lack an E horizon. Why? Well, we talked about that just a few minutes ago. Remember, they recycle calcium back to the surface. Calcium has that property of gluing the clay crystals together. When glued together into larger PEDs, they are no longer mobile in the soil, and so you don't get that rapid translocation of clay downward, and so you have less translocation of clay, higher pH, thicker black A horizon, all properties that we more or less associate with mollisols. I just put this in up here at the top because this is the former classification. This changed right around the time that I started studying soils, right around 1980. Some of these old classifications, prairie soils were Chernozems and Brunozems, and forest soils around here were gray-brown popsalics. You still heard those terms still in use, but the words mollisol and alpha sol were beginning to displace them. Just two different ways of classifying the soils. Now universally people use this more modern classification of alpha sol and mollisol. We have histosols. We'll look at a couple of these today. The bog peats, poorly decomposed, so a lot of fibrous organic material is still in there, generally formed from sphagnum moss and whatever plants are growing in and around the sphagnum moss. And we have finely decomposed black greasy soils called mucks that occur in our fens in the Chicago area. Histosol, the prefix referring to the organic matter. So not all wetlands have organic soils. In fact, most wetlands don't, but sometimes they do, and we have this soil order to describe them or to categorize them. And intesols are a group of soils that really haven't had much time to form because parent material is constantly being added to the soil. So most of our upland soils are glacial soils, and so they're anywhere from 10 to 18,000 years old around here, depending where you are in the Chicago area. But an entisol may form in an alluvial situation where you have layers of sands and pebbles formed by a stream, but it's still, the stream is still there, the stream is still depositing materials at flood stage, and so there's very little soil formation, little change at the top. You have an A over C profile. When you look at a sand dune, you'll see, if you look really closely, just a very slight change in that surface, but otherwise it's just a pile of sand. So what I want to do now is just to show you some of the soil sampling tools I use as an ecologist in the field. What I want to do for you right now is to just show you some of the soil sampling tools I use as a part of the job. This is the one I used for the soils that we've looked at, or will look at in the workshop today. This is called a Dutch auger. It has a screw bit on the end. It is probably the most versatile tool. It's not very heavy. It's easy to carry in the field, and I can use it in a very wide range of soils, from clay-rich soils to something like a sandy loam. You get into pure sands, they're a little not cohesive enough, but in most soils you can use this one. Now, if I have a really, really sandy soil, I can use this, which is a type of bucket auger, but you can see the openings at the bottom are not terribly large. The sand moves in but can't fall out. I don't use this very often, but I can use that in a pure sand soil, say if I'm working in sand dunes. If I'm working in a wetland soil that's organic, I will use this large gouge. It's very heavy, so you certainly don't want to carry this in the field with you wherever you go. But the giant, almost cartoon-like hammer here, you just pound this thing into the ground. With an organic soil, it goes in fairly easily. You then turn it. That breaks it loose from the soil, and you just pick it up, and your soil sample will be right in the middle of that gouge. So it works very well in organic soils like peats and mucks and fens. It doesn't work very well in mineral soils. The soil sampler I use actually quite frequently, but not so much for this workshop, is this little push tube sampler. Very light, easy to carry. I can take it apart and put it in my work vest or coat. And this one you simply push into the ground. And I can pull it up and you get a nice tube of soil there. That works very well as long as the soil doesn't have any rocks in it. So in soils derived from glacial till, where the pebbles tend to be very small, generally with 1 or 2 tries you can get this in, and you can go down wells. You can fill in more extensions and go as deep as you want, as long as the soil is moist. When it hardens at the end of the year, then you'd have to weigh 500 pounds to get it into the soil. But in the springtime, when you want to do most of your upland soil sampling, this works very well. It's light, it's easy to carry. It just gives you a fairly small sample if you're using it for teaching purposes. One fancy device here I just thought I would show off. I haven't used it in a while. It's a bulk density sampler. So it works sort of like that push tube, only it's much, much larger. And what I would do is just put it on the ground and hammer it in with this slide hammer. And then you pick it up. The soil is inside. And then you simply unscrew this device. You soil will be right inside. You can take it out. It will be inside of these 2 aluminum rings. Cut it with a sharp knife on both sides, put it in the plastic bag, and you can take it back and dry it out and weigh it to figure the weight of the soil. You know the volume of the cylinder, and so you can figure out the density of the soil. Very, very important if you're studying areas where soil compaction is an issue, or you have reason to believe that soil density is changing from place to place, and that's important. So those are the soil sampling tools I typically use when I'm out working as an ecologist.
Nest here? Yes, sir, Chief. I did ask for 2,000 agents this time. There's a lot of soil out there, Chief. I know the border thing with Canada looked bad for the Bureau. Fiasco is a little harsh, Chief. Yes, well, we did find several large undocumented rocks. Yes, I know. Yes, I know, Chief. They were just rocks. Yes, Chief. Well, it's different this time, Chief. The boys at FSU assure me there's something going on out there. I know I'm not supposed to use the word boys anymore. I know, Chief. Yes, there are women who work in the FSU. It's a manner of speech, Chief. Yes, I know what HR said last time. Not again, Chief. What do you mean no agents will work with me on this hole in the ground thing? No one? Somebody in witness protection? That's all I'm gonna get? Well, okay, well, who is he? Oh, it's not a he. This could be dangerous work, Chief. Lasavio. You don't mean not her. I mean, what she did to those 2 New York guys back in 2011, that was brutal. It's her or nothing. All right, Chief. I'll do my best, Chief. Yes, goodbye.
My name is Francesca Losavio. Really. I ain't got any idea what I'm doing down here, but my present employers told me that I needed to work with this nest guy. I'm supposed to keep track of anything that moves. Something about horizons and changes in texture, he said. Pretty sure he's lost it. I can tell you, it's pretty dark down here. Very dark, as a matter of fact. If you want to know the truth, I can't see nothing. So I don't know if anything moves. But it's okay, really. At least no one's watching me here. Big Frankie, my former employers was looking for me to talk. It's quiet down here. Yeah, I like that.
So, time for an intermission. Or questions. Ask any questions you like, or take a little break, get something to drink. Yeah, we'll be back in 10 minutes. I'll be here through the whole intermission, so you can ask any questions you'd like.
So we'll start up again at 11 a.m. And remember, you can ask questions by typing it into the chat, or you can unmute yourself and just ask it. We had a comment that says, these videos make me so happy. So thank you, Sarah.
So it makes you happy. That's good. It makes me happy every spring when I go out for the first time and feel it in my hands. It makes me happy.
We had a question. Which auger would you recommend for sampling prairie soil? Well, prairies can grow in a lot of places. It's really more about the parent material of the soil that if it's gravelly, you really
none of those things that I showed you work very well. You got to be pretty. First of all, you can usually tell a gravel soil just by looking for the exposed gravel at the surface, but you're going to have to look for an area of relatively disturbed soils and dig a small soil pit, and it doesn't have to be very large, depending on the slope, to confirm that it's gravel and at least test some of the properties of those upper layers. What I typically do when I'm working around gravelly soils is to look for woodchuck burrows. They always bring the lower material up. Now, if I'm working in a finer textured material, then a push tube sampler works very well. That the push tube sampler I showed you is made by Oakfield, and the set that I showed you, I looked, and some of these soil sampling tools cost quite a bit of money. That's $200. You can buy push tube samplers for $50 that probably would suit most people's purposes. I use forestry suppliers for a lot of my stuff. I generally find they're pretty close to the cheapest. They're cheaper than most other places where I find the soil sampling stuff. So they do cost some money, but you want to be able to get down about 20 inches to at least see the upper layers of soil. You don't need to go down 6 feet to see the interesting part of most soils. You can see that in the upper 20 inches. So a push tube sampler is probably a good place to start. And you can find those at forestry suppliers, a wide variety of them.
I had a question, where is that big hole from? What is it, a sinkhole? Followed by what and where is the big hole that Francesca fell into? So I just Googled a hole in the ground to see what kind of pictures we could get. There was actually a sinkhole in Russia. They called it the Gate to Hell. I'll put the story in the chat if anybody wants to look at that, because it was kind of interesting, but I used the pictures of the same location for that video.
No, I dug that hole, but
yes, Tom dug the hole. It took him all day. We had a question. Could you name the 5 processes again? She only had 3 in their notes.
Okay. Boy, this is going to be tough. Primary mineral breakdown, secondary mineral formation, movement of material in the soil, oxidation, reduction, and addition of organic matter. Is that 5?
Yes, I think so.
Okay, so primary mineral breakdown, secondary mineral formation, translocation of materials in the soil, oxidation, reduction, and then addition of organic matter.
Yep, that's 5.
Those are, when you think about soils and the soil layers, I think all of those processes are operating in all of the layers, but some of the processes dominate a layer. So addition and mixing dominate the A horizon, leaching dominates the E horizon. It doesn't mean other things aren't going on. B horizon is dominated by deposition, but it doesn't mean other things aren't going on. So yeah, it's a work back and forth between the profile, the processes, to try to see how they relate to one another.
Got another question in the chat. What would be the biggest difference between a typical local agricultural soil and a local prairie soil?
Well, let's assume that they were the same before the agriculture started. Typically, the agricultural soil, a plow generally mixes the soil down to about 8 inches. If it's very flat, then you're not going to get much erosion. What you'll get is a soil that has just been depleted in organic matter. That plowing up the soil and mixing the oxygen in there year after year after year degrades a lot of the organic matter. So you'll go down from 15% to 5 or 6% organic matter. Sometimes in an agricultural soil, you maintain it at that level with crop residues. But so you can lose organic matter from that just constant mixing. If the agriculture is on a slope, now you might have some erosion and some removal of materials from the surface, or alternatively, if it's the base of the slope, you could have addition of materials at the surface. So a number of things go on. with farming. If you're working in an X-farm field, you always have to be aware of movement. If there's any slope, you have to be aware of movement of material. So basins can be filled with sediment. So you might find a little wetland basin that doesn't look like a wetland basin today because it's all filled. So yeah, just be aware when you're looking at a soil that's been subject to agriculture that it has changed, lost organic matter, maybe eroded, maybe deposited on top. So all of those things can happen.
This is an interesting question. Has the soil always been, or was Earth one big rock after the Big Bang?
Well, soil, if the soil is an interaction, but it is by definition the interaction of living things on the surface of the earth. So until there were living things on the surface of the earth, there was no soil. There was sediment, there were rocks, there was piles of sand, but there was no soil. Soil happened when plants evolved around 400 million years ago and began colonizing the surface of the earth. So that's when soils, in the way that we use the term today, that's when soils really start. So there's a sort of, that's the Garden of Eden story about soils. They really happen as organisms start to colonize the Earth's surface, and we get that interaction between organisms and the surface. That's what we call a soil. So soils have not been forever. There were rocks here before soils and sediment, but not soils.
I have time for maybe one more question before we get started again, if anybody wants to put something in the chat or unmute yourself and ask. All right, I think we're good to keep moving on. Then again, if you guys have the questions throughout, feel free to keep adding them to the chat and I'll interrupt them for you.
Hello, I'm Ava Lachey, and this is OMG TV. We're joining the cast of Hole in the Ground today for a special On the Set Extra. Tom, what was your inspiration for the hole scene?
Well, I often dreamed of being a PED, a sort of medium, subangular blocky PED with a firm consistence, nice 10YR44 color. I just wanted to fit in, that's all, be like everybody else.
Really?
Yeah, ever since I was a child. It seemed so peaceful.
Well, thank you. So, Jackie, how did you prepare for the role of Francesca? What do you mean prepare? What exactly are you saying to me? I thought you were playing Francesca. You think I don't know who I am? But you should be careful what you say. Who is this Jackie person you speak of? Do we have a problem here? Is that a problem? Well, that's all we have time for. From the set of Hole in the Ground, we'll see you next time, I hope, with another exciting On the Set interview.
So this is going to be the fun part of the day today. This is where we'll get to go outside and look at soils in the field, which is always the most fun I have, is going out and just looking at how soils change from one place to another in the landscape. And if anything I want to get across to you is that they do change as you move through a landscape, sometimes dramatically over very short distances. And that when people will ask me, well, is it a prairie soil or a forest soil? And then, those two categories are useful categories if you understand them as a prairie soil as a soil that formed primarily under prairies, and a forest soil is a soil that formed primarily around here, savannas and woodlands mostly. But that sort of dichotomy sometimes gets in the way. What we want to do is to look at the site, to look at how soil varies across the site, and then make an interpretation. I'm going to do that over and over again today. Hopefully get that across. These are the four things that I, as an ecologist, I typically start off with. It's tiny little quick story. When we were putting this presentation, or really just starting it, I said rather full of myself to Jackie, well, what I'm not going to do is to tell people the 4 things they need to know about soil, because there's so many other interesting things about soil. And then I put this slide together and I looked and there were only 4 there, and I felt a little embarrassed. So I added one here, which in truth should have been there to start with. We're looking at pHs. We've already talked about that, top to bottom. And if not with a pH meter, we can take a little acid and look for the free carbonates, the free calcium carbonate in the soil. So these are the 5 things I'm going to look for that are important to understand, for an ecologist, important to understanding soils, both what they were, what they are, and what they might be good for in terms of ecological restoration in the future. So we're going to start off just doing a bit of soil description, trying to put it all together from things we've already talked about. You see a Munsell soil color chart in the foreground.
So what we're going to do right now is to really look at soil description, top to bottom. I'm not going to try to make expert soil describers out of you, but I just want to show you how an ecologist looks at soil and use these 2 soils here as a demonstration. These were collected right along Route 31 in a nice little oak woodland, about 100 yards apart. The one closer to me was collected downslope in a bur oak savanna. The one in the background was collected upslope in a white oak woodland, fairly gentle slope separating the 2, probably 3 or 4% slope. So had you walked out there by yourself and hadn't taken this soil workshop, you would probably have thought, well, nothing really changes. It's a very, very gentle slope. And but when we look at the soils up close, we can see that they are in fact quite different. The one in the foreground just overall looks different, doesn't it? It's duller color, more dull brown colors in the lower parts of the soil, which are on the right-hand side. On the left-hand side is the topsoil. It's a bit thicker and darker in the wet soil, and the drier soil, it's a bit thinner and lighter in color. So those are some overall impressions. These are the kinds of things you get used to seeing when you work with soils in the field. And the relationship between these 2, we would call these 2 part of a catena of soils. Pretty word from soil science, C-A-T-E-N-A, catena, meaning it's 2 or more soils that are related to one another by changes in one of the soil forming factors. Here it would be relief, simply moving downslope. Parent material in both is glacial till. Time of formation is somewhere around 18,000 years. The organisms, it's an oak savanna in both cases. Climate, pretty much the same. So we're down to that one factor of relief, and here affecting moisture that causes these soils to develop differently. Now we're going to look more closely. The little pieces of white wire that I have here, this is obviously not Glacial Park anymore. This is my garage. And rather than picking up some sticks, all I could find was some bits of wire to use to separate the horizons. Typically when I'm in the field, I just look for some sticks and break them up. And it allows you first you get a sort of hypothesis where it is, and then you look some more and you shift them back and forth until you're satisfied that you've broken the horizons down about as well as you can. So here's our A horizon, zone of organic matter mixing. We're going to look at colors first from top to bottom, and you can see this is somewhere down around a 3.1 or a 3.2. Not as dark as some of those wetland soils we were looking at. It's about what you expect in an oak savanna. As we move into this second horizon, which will be our E horizon, the soil colors have moved up probably somewhere around a 4.3. That's a pretty good match right there. It's typical E horizon and oak savanna. And this is a sort of transition zone between the E and the B. And when we get down here in the B horizon, this first B horizon zone, we're probably looking at something over here in the 4.4 to 4.6 chips right over in here. Pretty typical soil. Now this is unusual. I think we're actually near a shift in parent material. It's getting a bit higher in gravel content down here. Soil's a bit hard. I collected it 2 days ago. And And you can see this soil is just red. It is redder than the chips on this page. It's not far from a 4-6, but let's go over pages to a 5YR page, which is a more red color. And I think that's probably a better match, somewhere around 4-4, 4-6, somewhere in that zone. I mean, so, but a well-oxidized color from top to bottom, no gray areas in the soil, modeling as it's sometimes called. And when we look at the somewhat poorly drained soil in the foreground, it's got a darker A horizon, so you're probably moving down to a 2-2 color or so. The E horizon here is pretty well, even more bleached in color, maybe even a little bit thicker. Pretty obvious when you see that color shift. Dark gray brown, very light gray color, and then this deeper brown color. And when we look in the B horizon here, this is a little hard to see with a camera. The areas of changing color are very, very tiny and aren't going to show up very well in the video. You can sort of see them going back and forth between something like a 4-4 here and a 4-2. They're going back and forth between these chips. Not difficult to see when you're out in the sunlight, but pretty hard to see here in this room. So there's some evidence of imperfect drainage here. There's some evidence of water standing in the soil up into this zone. I mean, just the overall colors of the two suggest some changes here. It's actually a little easier to see at a distance this time than it is when you get up close. And again, rock content's increasing here at the surface. Now, when we look at textures, again, this developed all from the same glacial till. What we expect to find here is what we find, which is a silt loam textures in these upper horizons. This is getting a little bit dry because I collected it 2 days ago. It was wrapped in newspaper, but still dried out a bit. But it has when you rub it between your fingers, it finally just reduces to sort of a powder. When we get down into the B horizon, it's much, it's harder for one thing. It started to dry out, so it's a very different feel. And when you can start to mold it, it stays together. You see, you know, the books will tell you to make ribbons, but as you start working with soil, you can see that it just molds and it holds little shapes. And as soon as you put your fingers on it and start to work with, you can feel that the pieces hold together more tightly. And then when you try to squish them, they still hold together. Bits and pieces hold together in these little lumps. So we're moving from silt loams down to the silty clay loam area in these parts of the soil. Typical transitions you would expect in a woodland soil. Likewise, with a somewhat wetter soil, the zones are a little bit thicker here, both the A horizon and E horizon, but again, really even a better, just beautifully developed E horizon, very smooth, silty feel. Silt was ground by the glacier down to the size of flour that you would buy in the store to cook with, and it feels, once it starts to dry up between your fingers, just like you're sliding flour between your fingers. If you get down to the B horizon, again, it's much more cohesive. It's a little bit moister than the other, so I can start to create those little thin shapes that you could never do in an E horizon, and they hold together pretty well because there's just so much clay in there. So again, our transitions in color from top to bottom and our changes in texture from top to bottom are about what we expect to see in woodland soils. I do have the dilute hydrochloric acid here. And when you test it, you wouldn't be able to see bubbles even if they were there because the bubbles are very tiny. But all I need to do is to drop a little acid, as they say, on the soils, and then you wait for a second and you look to see whether there are any tiny bubbles coming off of the soil. Now, if you get down into areas of gravelly parent materials, as we will when we do some of the soils in the park here in just a few minutes, definitely it was fizzing. Here we're not seeing any. Both of these soils developed under oak woodlands. Acid leaching has reached fairly deep. If I could get down another foot or two, probably I would get to a zone where the pH rises, and eventually you would start to see little calcium carbonate crystals in the soil, and that's where you get the fizzing. but it would be very deep. Both of these are fairly deeply leached soils. So those are two examples of soils, how you separate them into horizons. For me, the interesting and significant thing is how these patterns change as you move across the landscape, move from one parent material to another, move, in this case, just down slope from one site to another, and to see how the soils change. It's always easier to determine the significance of one soil if you see the soils around it. So what we're going to do right now.
Okay, so we're gonna visit a number of places in the park. The videos from here on will be done out in the field, a little bit less detailed than that one, but we're gonna go to Glacial Park Bog and look at the soil there.
This is the bog at Glacial Park. Surrounding the bog on the south end is now a restored prairie. Formerly that was a cornfield, probably for 100 years, and there's a lot of sediment on the south end of the bog for that reason. The bog occupies a kettle hole between two gravel ridges on the east and west sides. So any water that moves through that gravel is charged with lots of mineral nutrients and highly alkaline in nature, and yet the bog is quite acid. On the north end is a low marshy area and then more gravel hills beyond that. So the question we have is, how can you develop an acid wetland in a landscape where the water going through the surrounding hills is highly alkaline? Here's the core I removed from the bog, and first of all, there are two different soils here. The one on the left is a very highly organic fibrous material. This is the peat produced by the leatherleaf vegetation in the bog. It's about 98% of the vegetation in the bog is that leatherleaf mat, and you can see it's very fibrous, very little decomposed. Peat and sphagnum moss really make up most of that soil. And then there's a gap, literally a space, and then we get down here to the bottom, and we see this is almost pure mineral mud down here, meaning non-organic mud at the bottom, and right on top of this layer is a sort of mixture of inorganic mud and some fibrous material. So there are two questions. Why the gap? Well, we probably have over a foot more water in this bog than is usually here. I've gone out in the bog many times and I've never seen it quite this full of water. It was well over my boots to try to get into the bog. And when you're walking out there, it's obviously floating, and so the peat mat is now pulled loose from the bottom, and you've got about 25 centimeters or 10 inches of the peat mat is floating on top of the more mineral material below. Normally when I've used the gouge auger out here, what I see is a continuous peat mat, relatively thin peat mat over these muds at the bottom. The second question about this soil has two parts, and the first part is, why is it a bog? Because most wetlands in this part of McHenry County are marshes and fens and not bogs. So why is it a bog? Why does it develop this acid peat soil? And the second part of that question is, why is this peat mat so thin? If you look at the bogs at Volo Bog or Moraine Hill State Park, the Leatherleaf Bog there, the peat mat is tens of feet thick. And here it's now, this looks like about 16 inches, and I've never measured it more than a couple of feet. So why is the peat mat so thin? Was it always a bog here? So a couple of important questions. The first part of it I'll try to answer with some diagrams here, just in the next part of the presentation. But in considering the thinness of the peat mat, it's always seemed to me that the likely explanation, now this is my explanation, it's not necessarily the truth, it's my explanation, is that it wasn't always a bog. And that over at least the last 11,000 years with a warmer climate, it shifted back and forth between marsh and bog, depending on the fire regime, cultural activities in the region, whether or not the climate was warmer as it was 5,000 or 6,000 years ago, or cooler and wetter as it was 1,000 years ago. So these are all influences that might have affected whether it was marsh or bog. But something is certainly going on here. This is a very shallow peat mat and a very shallow kettle hole between two gravel hills, and yet it's a bog.
So what I want to do is just to quickly go through, I mean, for me, the interesting thing about soils is the stories they tell. And so I want to go through a little bit just to talk about how a bog, an acid bog, can form surrounded by gravel hills where all the water that goes through those hills is highly alkaline. Well, first let's just talk about how a lake works. When the glaciers left, there were lots of little ponds of water. Most of them remain ponds of water, and there are ponds of water today, lakes, ponds, because glacial landscapes are relatively poorly drained. They just have depressions in them. Kettle holes are just depressions in a moraine that don't drain anywhere, and water sits there at least seasonally. So why didn't all of it turn into bogs? Well, in a normal lake, you have a circulation. In the fall, when it gets cold, that surface layer of water cools and gets denser. It sinks to the bottom, and when it goes to the bottom, it takes oxygen with it. When it goes to the bottom, it pushes nutrient-rich, oxygen-poor water from the bottom to the top. So the lake turns over seasonally. Also, wind and wave action can just mixes such that you never get conditions in the bottom of this basin that are really conducive to just piling up more and more organic matter. It's decomposing. So lakes can be lakes for 18,000 years and have no organic sediments at the bottom. In fact, they just fill in with clays, and we're going to look at a lacustrine clay soil a little bit later in the presentation today. Just fine sediments that wash in from the surrounding area and settle in the bottom of the basin. Likewise with ephemeral ponds, where the water dries down, it's a pool of water, so you get some circulation, but you also just get the fact that it dries down and the oxygen-rich atmosphere comes closer and closer to the surface and really doesn't allow a perennial buildup of organic matter because the oxygen just allows its decomposition. And likewise, you have surface flow and typically a glade. Remember that word glade just means very, very gray mineral mud, very, very poorly oxidized, so you get those gray colors. But let's turn back to the lake and ask, well, why do some lakes do turn into something else? Well, if you have a lot of groundwater coming to the surface in the surroundings of this lake, lots of mineral nutrients in the water, you can fuel really, really rapid vegetative growth around the edges of this. And if the plants grow fast enough, you create enough organic matter, it starts to form just mats of dead vegetation floating in the water and sinking down into the water. And what's happening here is it's sort of clogging up the water column such that it doesn't circulate anymore from top to bottom. It's exactly the same phenomena that is the reason why you wear a thick coat in winter, because that fabric or the goose down or the polyester filling blocks the circulation of air from the surface where it's cold to the inside of the coat where it's warm, and it blocks the heat exchange. Here it's blocking water movement and the oxygen exchange from the surface to the base. And so what starts to happen is the organic matter that sinks to the bottom doesn't decompose. There's no oxygen down there, so it starts to build up. And as it builds up, it starts to build this sedge peat mat, building up toward the surface until finally it builds up right to the water table surface. And at that point, at least in a pre-European settlement landscape in Illinois, fires would have come by every few years and burned off the vegetation that crept across that peat mat. Or you might retain a sedge peat at the surface or develop into a muck soil. Either one is possible. In international wetland terminology, you would call this a poor fen. It's one of those pejorative terms like fault Solomon seal. You kind of wish our language didn't work that way because there's nothing poor about these. They're beautiful wetlands. Poor simply means slightly more acid than a spring fen, which we'll look at next. there's a beautiful poor fen on the far east side of the Morton Arboretum where I used to work back in the 90s. I did a lot of work there in deep peat and muck soils there. If one of the interesting things about this is it's flat. That I remember that wetland at the Morton Arboretum, and I would take my helper out there and my builder's level and go across the surface. It was just dead flat across the surface for the obvious reason that it grows up to the water table, fires burn it off, and so it's dead flat, meaning the vegetation isn't zoned the way it is in most mineral soil basins, which are shaped sort of parabolic in shape, concave basin, shallower along the edges, and it gets deeper and deeper as you go in. And so it's zoned plants that can thrive in this deeper water from the innermost zone and out to the outermost zone. So it's that bullseye zonation of vegetation is typical of mineral soil basins. So when you look at a basin and you see that bullseye formation, you're looking at a parabolic basin, probably a mineral soil basin. Sometimes you can start off with a poor fen. I remember finding one at Pleasant Valley that they, in the agricultural, through the agricultural period, there had been so much sediment poured into this that it collapsed in the center and started to look like a mineral soil marsh. But the two in their original condition have very different zonation of vegetation. Spring fens form along the sides of this gravel hill. Remember, if you were there with the geology presentation, so we're part of ice contact topography, kettle kames. Here is a kame. The water pours into the gravel. It goes down till it meets a permanent water table and then starts to move laterally. It's always by gravity, but it moves laterally and then comes out along the side of a hill. Often this is induced by a clay layer that stops vertical movement and forces the water to move laterally. So depending where that clay layer is, sometimes you can get wetlands way up on the slides of hills, far above the bottom of the basin. These spring fens, which is usually when people just use the word fen in Chicago where they're talking about a spring fen, develops its finely decomposed muck soil. And it's probably the most vegetative, just in my experience, the most floristically diverse ecosystems for good reason, because they're sub-irrigated. So wetland plants never have to have their roots dry. So lots of wetland plants grow in here, but they're never, because they're on a slope, they're never ponded in water. So upland plants can get just enough oxygen to stay alive. So you get a wonderful mix of prairie, sort of typical prairie plants in with a rich wetland flora, and it's just marvelous places to botanize in these spring fens for that reason. And if you look in the soil, you'll find it, and we'll see that kind of up close and personal here in just a minute, the black fen soils. Bog formation happens when that what we called the poor fen, full of sedge peat, isn't under fire influence, and so the peat mat, if sphagnum moss, just a little bit of sphagnum is brought in there by birds or whatever that are visiting the wetland, and it starts to grow, and it grows up above the groundwater table. And when it gets above the groundwater, it's rainwater fed. So you can develop this, and the rainwater is acid and very nutrient poor, so you can develop this sort of two different wetlands. You have a wetland that's perhaps under groundwater influence here that's alkaline and nutrient rich, and perched right on top of it is a sphagnum and a wide range of other plants that can grow in the sphagnum that love that acidity, perched right on top of it. The key to this distinction is the fact that water moves through the bog mat and down. It doesn't move up from the groundwater down below, it moves down. So this is a rainwater fed, nutrient poor acid system above, at least partly groundwater fed, more alkaline, more nutrient rich wetland below. So let's look out in the Nippersink Valley and see where first thing we're going to see is a fen along the edge of the valley.
We're out at the edge of the Nippersink Valley now. See it stretching out there, probably a half mile across the valley. This would have formerly been prairie, wet meadow, marshes throughout the valley, right next to Lost Valley Visitor Center, which sits on a big gravel hill. Now the pond between Lost Valley Visitor Center and myself right now was dug somewhere in the middle of the 20th century to provide water for fire control in the building that preceded the visitor center. So we've taken a look at the soil here, and what we're standing on now is a fen, a spring fen, meaning a groundwater discharge wetland. The water is going in that gravel hill and coming out along the base of the hill, and what it creates is this very highly organic but very highly decomposed soil. It feels sort of like grease between your fingers. Just a little bit of fiber here and there, but almost completely decomposed. Just black, greasy organic matter. There's a little bit of mineral matter in there, but most of it is organic. Now this happens because the dominant vegetation here for many thousands of years were grasses and sedges in a sort of ideal environment for rapid growth. So you have a sort of sub-irrigation system, plenty of sunlight, lots of nutrients coming up with that water coming out of the ground, calcium, magnesium. And so the grasses are growing extremely rapidly. They're creating lots of organic matter below ground with those fine roots. And so the soil literally grows upward by the addition of organic matter and increases in bulk, and it continues to grow upward until the surface gets dry during the late fall, and then the frequent fires coming off of the prairie would have burned off that surface. So fens form in those groundwater discharge areas in ice contact landscapes where you have these gravel aquifers feeding the groundwater, which then discharges along the base of the hill or along a hillside. If you've got a clay layer in that directs the water to discharge along the side of a hill, and you get this what's called a muck. It is you might, if you use peat as a sort of generic word for a mineral, for an organic soil, this would be a muck, a very descriptive word. You wouldn't want to be hit in the face by this muck, very black, greasy stuff.
So you'll see that black muck soil. That's something always to look for. I mean, in videos and pictures, you can't discern colors as well as you can out in the field, particularly if you've got just the right lighting conditions out in the field. I mean, this is jet black. There's enough carbon in there. It's just jet black. It's not very dark brown. It's black. So you probably got anywhere from 30 to 60% or more organic matter in there. There's often just very fine amounts of clay left in there, but it's just jet black in color and black and greasy and very different than the stickiness of clay. This just feels slippery and greasy.
On the Nippersink Valley now, and when the glacier retreated in this area, retreated to the north, which is in this direction, there's a lot of evidence that a shallow lake formed in the valley, and that evidence is right at my feet right now. What you're looking at is a lacustrine clay soil. Now the word lacustrine means the sediments are derived from a lake. We don't know of any lake in recent history, but there's a lot of evidence that a lake formed here probably shortly after the glaciers moved away. This soil is very, very plastic, meaning you can just mold it all you want. It's just like the modeling clay you worked with as a child. It's just this particular piece I'm working with right now is a little bit too wet to keep molding. You can just see you can do almost anything with it you want, and it holds together pretty well. You get all sorts of little ribbons and sheets working with this soil. So it's very high clay content soil. You can look at the colors are very dull. If you look at your Munsell chart over here, they're coming out on about a 10YR31 color, which is that chip right there. That's a very poorly oxidized soil, which is what you would expect in a soil that is seasonally very wet, high clay content, very little way for oxygen to migrate down in the soil to that depth other than through the vegetation. And what I can show you right here, and I hope you can see it, is a root oxidation model. And I'm going to try to move the model around. And I can't see it through the camera right now, but hopefully when I look at it on screen a little bit later, I'll be able to point it out to you. The root oxidation model is formed as the grass and sedge vegetation has to transport oxygen from the surface downward to keep the roots alive, and some of that oxygen escapes into the surrounding soil. I'm going to turn around and put it in the shade and see if that helps. Root oxidation models are one of the diagnostic features of wetlands, where wetlands occur in these areas of mineral soils.
So that was a neat find. I mean, depending where you go in the Nippersink Valley, it's a big flat valley, and you think everything's the same. Well, oh my goodness, you can find all sorts of things that have happened in the Nippersink Valley. The stream has occupied so many different channels. The lake sediments are left here and there now. So it's a wonderfully diverse place. But this is a great example of a soil formed in lacustrine clays. You can see dominantly sedge vegetation in this area.
We're in the Nippersink.
Whoops. Oh, no, this is it, yeah.
We're in the Nippersink Valley again, and we're in the inside of a meander bed. I'm looking south right now. Now I'm looking west, and now I'm looking north. And I came into this meander band for a particular reason. In fact, you can see the Nippersink doubles back on itself. You can see the channel both as it's flowing east and then as it's flowing west in the background. I'm in the middle of this meander band for a good reason, because when you're in the middle of a meander band, you're in an area where the soil formed from stream deposits probably in the last few centuries. So let's take a look at it. Just at a first quick glance, you can see some things about soil we've been talking about. You see that the surface on the left-hand side is a sort of darker brown color enriched by organic matter. You can see that the middle zone is a little more brown in color, a little more oxidation. And you can see on the right-hand side, the soil gets very dark gray, where it's glayed by prolonged water saturation. But let's get a little bit closer and look at the soil. This soil here, while it's smooth to the touch, isn't anywhere near as sticky and clay-rich as that lacustrine soil. These are flood deposits of the Nippersink, probably dominantly silt, some clay, a little bit of fine sand. So when the Nippersink is out of its banks, the water slows down and this fine soil settles out on the surface. That's really most of the rooting medium, or at least a lot of this A-horizon, is that flood deposits. As we get into this second zone, the soil is a very loose sand. Once you break the clods up, it molds a bit, so it's somewhere between a loamy sand and a sandy loam. These are old point bar sediments. So right along the inside of a stream bend, there are sands deposited right on the edge, and as the stream keeps migrating, in this case to the west, it leaves behind point bar sediments. These are well-sorted medium sands with just occasional coarser grains in them. And we get all the way to the bottom, and we've got a very coarse sand and little mollusk shells that look like little snail shells, maybe some little baby mussel shells in there, but a very coarse sand. So this is probably the in-stream deposit. I mean, I don't want to get into trying sort of fanciful, detailed interpretations without doing 3 or 4 more cores. If I could go down another few feet, I'm as deep as the auger will go today, I might change that interpretation. But this is certainly at least some sort of in-stream deposit. The coarse sands, the mollusk shells, obviously, that happens in an aquatic environment. The colors in this middle zone are sort of going back and forth between something like a 3-1, a very glade, indicative of a lack of oxygen, and then something over here, maybe a 4-3, maybe a 5-3, so something showing a bit more oxidation in this loamy sand, sandy loam layer. Frankly, I mean, the water is really high right now, so it's much wetter than it is throughout most of the summer. And here, even down around almost 30 inches, you can see some bright orange. That one probably would even take us over to a 5YR page at least, because it's so red, and probably somewhere up in the vicinity of a 5.4 color on that 5YR page. So you get some zones of oxidation, even fairly deep, because this soil dries out a lot during the summer. Right now it's quite wet. So there's a sort of typical wetland soil with a series of different deposits, really about different stages in the history of the stream.
That was one of my favorite soils from the day. I did most of these cores in one day. That was a perfect one there. Now we're going to visit just a prairie restoration. If you're familiar with Glacial Park, this is on the east side, just east of Pioneer Road. A prairie restoration from a distance just looks like fairly homogeneous prairie. Well, let's look at the soils. We're going to start at the top.
We're in a prairie restoration east of Pioneer Road, just north of Nippersink Creek. We're in an area where geologically this is part of the glacial moraine, sort of gently rolling landscape, a little hard to appreciate in a picture like this, where it's mapped as glacial till over a gravelly outwash deposit. The brush behind you hides another feature that you can't see, which is a fen, which is probably, is in my memory, about 100 meters into that brush, 110 yards into the brush. My hope in coming here, it's always my hope to get a nice simple interpretation for educational purposes, but nature almost never does what you want it to. Here is the soil that I pulled up down to about 30 inches. Now this is up high on a hill. This was farmed for a long time, so you would expect this to be a highly eroded site. And yet we have a very deep, organic rich A horizon, which requires a little explanation. All right, let's take a closer look at the soil here. We can see a very dark brown surface, probably down here on our 10YR. The wind just turned my pages for me. It's nice of it. There we go. Down here on our 10YR 2.1 chip at the bottom for this surface. Very organic, rich surface. Probably less so, though, than it used to be, because this has been plowed for 100 years. Mixing the soil, introducing oxygen would have degraded organic matter. Erosion would have removed it from the surface. So we've probably got a much less organic rich surface than it used to be. So I'm suspecting this was actually old fen ground. If we actually go to the bottom, we can see a clue to that. Remember with a spring fen, we need a water source, and here it is. This is a sandy loam to loamy sand material, full of gravel, really right at that contact between the glacial tills above and the outwash gravels below. So the outwash gravels being the aquifer that move water from higher on the slope to my southeast in the direction of this site. Coming out here, you get a bit of a transition zone in between the two. So this is certainly an old prairie site fed by groundwater. I suspect it was actually a fen site in the distant past. Yeah, we're going to move downslope a step at a time and see how the soil changes, and we'll end up with a fen all the way at the bottom. Okay, so we've moved about halfway down the slope now. We have where our site is probably around a 5% upslope grade and about 1% downslope grade. So we're in a sort of convex position on the slope that may be important. Let's take a look at the soil here. We see a pretty dark, deep, organic rich layer, at least down into the 11, 12, 13, somewhere in that transition here to about 18, and then moving into what's clearly B horizon. Classic sort of prairie soil. In fact, this surface might be a little thicker than it used to be, because given this convex position on the slope, there's probably more sediment coming into this site than is leaving it in erosion. But in any event, a sort of classic prairie soil developed in glacial till all the way down here at the bottom at 30 inches. We can take a close look at this, and you can see some little pebbles embedded. It's a sort of clay loam, silty clay loam material, little embedded pebbles, classic glacial till. There at 32 inches, you can see the colors. Yeah, I know this is hard. It's not, well, it's not too hard for me, for you, probably pretty difficult. But you can see dull colors there, somewhere around a 4.2, 10YR 4.2 color, and some really bright orange flecks in there, somewhere around a 5.4. So indicating going back and forth between oxidation and reduction depending on the time of year. In fact, you really can't see anywhere on the soil. We can come up here into this transition about as high as we can go before the soil color is dominated by the organic matter. You can start to see some root channels in there. See those dark sort of stripes in the soil? Those are root channels. Let's break it open and see what you see. Again, a mixture of colors. Most of the colors here, again, are fairly dull, somewhere around a 4.1, 4.2 color, and some bright flecks, again, somewhere around 4.6 or so, indicating back and forth between oxidation and reduction. Sort of classic soil, that prairie soil. For a mesic prairie, a fairly flat site, water stands here on this heavy glacial till, so it only spends a little while, and during the summer, late summer, where it's really dry.
We're gonna go skip that next one and go right to a kettle came ice contact terrain, just to get a nice contrast. So we're looking at a bur oak savanna and the sort of the southern part of Glacial Park.
I'm in a kettle hole here in Glacial Park, sort of the south part of the park. You see the steep slopes of the sides of a kettle. There's the kettle bottom right there. So I'm going to go into the side slope to see what we got for soil here. And you can see it's fairly dark in color. Pretty rich in organic matter, very loose soil, probably a loamy sand in texture, going down at least 10 inches here. So you would probably classify this as a mollisol. I mean, this would come out as a Rodman soil series, which is classed as a mollisol, but that would be kind of ignoring. I mean, it's really not a mollisol. It's not a grassland soil. It's a soil that developed under bur oak savanna. So sometimes that sort of binary classification misses the point here. This soil is what happens in a bur oak savanna in an ice contact landscape. Now let's look. We can look a little deeper. I didn't want to dig a huge hole here. Just no need to create such a disturbance. But the groundhogs don't have any problem creating a disturbance here. They dug a nice deep hole and brought up all the cobbles from down below. Pretty obvious. This is a water deposited glacial outwash sediment. So next we're going to go down the slope, down into the bottom of the kettle. Let's see how the soil can change over just a short distance. We're in the bottom of the fen now. Looking upslope to the west there. And when we look at the soil, we see something that, well, maybe you wouldn't have expected. We're in obviously historically a bur oak savanna ecosystem, one would assume for many thousands of years, and yet this doesn't look like the woodland soil I promised you earlier in the presentation when I said A horizons would be thinner under a woodland soil. So maybe I was wrong. Or maybe the other thing I said, which is you'd always interpret a soil in a local situation and never just think about one factor at a time. So let's look at this. What we've got here is a stack of sediments that have come off of these steep surrounding hills. Now those gravel hills would erode very, very slowly in a pre-European settlement landscape. But then again, it's a very steep slope, and you've had 18,000 years. And so some of this accumulation was just sheer time and very low rates of erosion. So the sediment was accumulating fast enough, faster than the organic matter,
was degrading. And the other thing is, in the relatively recent past, for about a century, this would have been, or for at least a century, this would have been grazed by cattle. And that would have speeded up rates of erosion, probably several orders of magnitude, the cattle hooves chewing up the soil and allowing heavy rains to move it down slope. Whatever the effect, this is the effect of relief in parent material, not the effect of organisms. You remember the 5 soil forming factors: climate, organisms, relief, parent material, and time. Well, this soil is really not a product of vegetation as much as it is a product of relief and parent material. If we look down to the bottom, we can see a reasonably well oxidized soil, even almost 40 inches below the surface. Because we're still high in the landscape, even though this is the bottom of the kettle, it is not in any sense wet. When we look at, there's prairie betony here. We've got some wood anemone, Pennsylvania sedge, plants you expect in a well-drained woodland landscape. So, yeah, soils can change a lot in a short, two morals, soils can change a lot in a very short distance, and don't get the idea that you can make the world simple by looking at it as if there's one factor that determines the soil. Here, it's parent material and relief that are really dominating soil formation. So, yeah, this is kind of the conclusion here. What I want to leave you with. There's 5 factors of soil formation are. I mean, I'm not just saying these. This is actually what goes through my mind when I'm trying to interpret a soil. Every time I look at a soil, I'm asking myself, where did it come from? Why does it look the way it does? You have to think back and forth between all of these different factors. And I just run into time and time again people trying to force a one factor interpretation. Typically around here, they're wanting everything to fall into these 2 rigid categories of prairie soil and forest soil, when those are obviously 2 categories, but the range of variation in each one is enormous, and they overlap in practically every property, which is beautiful. But you need to look at that. You need to look at the individual situation and think back and forth across all of these factors to really understand what you're looking at. Use secondary sources to learn what to look for. Jackie gave you a lot of information about the NRCS soil survey. Incredibly important stuff. I mean, I always look at that when I go to work in a new place. But I look at it in order to get a set of expectations for what I might find, and then I go in the field and look. Typically, these surveys don't give you good interpretations. Often we want interpretations in ecological restoration that are at a fairly fine scale of resolution. This is important to us. We're paying a lot for seed. We're putting a lot of effort into it. And to really interpret soils at that fine scale, you need to look at them in the field. And don't pretend to be an expert based on one source of information or standing at one spot in the field. I'm always sort of forced into this when I teach, because I can't keep people out there where I do 6 cores. But typically, if I'm working in a landscape and trying to understand it and interpret it, I move back and forth, up and down the slopes, back and forth, to try to understand how do the soils vary in this place. And once I understand that, I typically have other information I can look at. Where's the evidence? Tell me where the remnant woodlands and where were the prairies prior to European settlement? Where could the boundary be? Work my way back and forth across the boundary, trying to understand how to interpret the vegetation that's there, not just drilling one hole in the ground and making up a story. So with that, there's the moral of the story. Soil is beautiful, and enjoy it. So with that, I'll open it up to questions.
I wanted to add a quick note about if you wanted to look further into the web soil survey that is freely available online. The webinar that we explained that in was called A Step Back in Time. You can find that on our YouTube channel at Discover MCCD under the Tom Talks playlist, which is where this will be posted once we get it up, probably on Monday. And we do have a couple of questions in the chat for you.
Okay.
How long would it take for the soil of a restored prairie to resemble the soil of a remnant prairie?
Oh, that's a good question. You know, it depends on the situation. Probably it's a matter of, you know, centuries, not thousands of years. It depends kind of how depleted the original or the soil that you find. Let's say it's been in agriculture for 120 years. It's been depleted in organic matter. Rebuilding soil structure typically happens fairly rapidly over a matter of decades. You know, building the organic matter up, you know, increasing it by 10% will probably take many decades to a few centuries. But I mean, soil, those kind of properties will redevelop. It's not that soil has been changed and altered forever and it will never ever be the same again. So the soils will rebuild themselves over time. You know, some of that will happen during your lifetime and mine. Others will require another few generations of people.
Another question. Would you explain relief again?
Relief is just changing the surface shape of land. You might call it topography. So you go from the top of the slope to the bottom of the slope. The description of that, you know, the elevation from top to bottom, that's called relief in a landscape. A high relief landscape has lots of steep hills and lots of changes in elevation. A low relief landscape is fairly flat. So that's what relief refers to.
What is the difference between a sandy loam and a loamy sand?
Well, if you look, when you go back through the PDF of this, you'll see that the loamy sand is kind of closer to the sand, to that corner of the triangle, the textural triangle. Loamy sands just have more sand than sandy loams. You can make a loamy sand into a sandy loam by just adding a little clay to it.
All right, we got several thank yous for a fascinating presentation and bringing soils alive.
Well, so
And if anyone has other questions, feel free to add them in the chat or unmute yourself and feel free to ask.
Hey, Tom,
yeah,
I got a question for you.
okay.
It's
What's that?
probably out of your area, but I think I've been spending too much time social distancing. So here it goes. Why do some kids eat soil? Is it for nutrients? Is it in their DNA? And did Adam and Eve live off of apples and mud pies?
I don't know. Well, not sure why some kids eat it. Actually, soil. Interesting, quick story. Read a story by anthropologist Claude Levi-Strauss, who worked in South America back in the early 20th century, and there were tribes of native peoples there that ate soil with their organic food, and no one knew why they did it. And of course, Europeans, being Europeans, looked down on them and called them the dirt eaters. But it turned out that they were able, by eating soil, they were able to eat plants that were poisonous to Europeans, because the soil, the particular clays in the soil, would chelate the poisons, and they would just move right through the digestive system and not kill them. So the soil eaters, I'm not saying this is why children eat soil, but there are actually cultures where they will take soil can detox certain plant toxins. So yeah, I don't know. I'm not sure why certain kids eat soil. I played in soil, but I didn't eat it, as I know.
Okay, thank you.
Another question from the chat. Is it true that in a prairie restoration on a glacial moraine that plants will not penetrate the clay layers?
Well, the clay layers in a glacial moraine, the clay layers, I mean, depending what you mean by clay, the B horizon is very high in clay content, and certainly plant roots penetrate that. My point is that in morainal landscapes where you have fairly deep deposits of glacial till, by the time you've gotten 30 or 40 inches down, it's basically like a piece of concrete. It's massive. There are no cracks and crevices in it. There's not particularly any water or nutrients down there. I mean, calcium is pretty abundant in the soil. There's no reason to punch holes in glacial till to pick up calcium. So plant roots Plant roots are very plastic. They move and depending where you plant them, they move in the direction of water and nutrients. And in typical glacial till site, there's just no reason for plants to try to drill into that stuff. There's nothing there for them. On the other hand, on ice contact landscape where you have deep gravelly and sandy soils, yeah, those roots can go down many feet in search of water and nutrients.
Anybody else have other questions?
Well, I want to thank everybody for coming today. It's always fun to talk about soils. Yeah, I had a big kick going out in the field and gathering the stuff, and I had to get a big kick about talking about it. So thank you for coming today. And thank Jackie always as the great organizer, the brains behind the whole operation.
All right, and stop recording.